Okay, so for this last section of Unit 8, we're going to talk about how reactions occur. What's actually happening? We're going to be thinking more in terms of a molecular level. What's actually happening to the molecules? And so, in order for molecules to react with each other, they have to come in contact with each other. They can't react from far away. So they have to actually collide with each other. Molecules are moving around everywhere around us. If it's in a liquid, they're moving around. If they're in a gas, they're moving around. They're constantly colliding with each other. However, not all collisions result in a reaction. So in order to have a reaction, we have to have an effective collision, or a collision that does result in a reaction. So to be an effective collision, first of all, the molecules that collide have to be the correct reactants. So the correct reactants have to collide with each other. They also have to have the right orientation, and they must have the right amount of energy. So let's look at all of those. All right, so first of all, why are collisions necessary? Well, they can't react unless they come in contact with each other. Then what happens during a collision, as they get closer and closer to each other, they're going to form some new bonds. And they're going to break bonds because, of course, the atoms are rearranging with each other. So they have to break some bonds, and then atoms are exchanged and new bonds are formed. Now, why does there have to be a minimum amount of energy? Well, it turns out that you always are required to put energy in to break a bond. It doesn't matter what kind of bond it is, because these electrons are holding atoms together. In order to pull them apart, you have to put energy in. Energy is always required. Now, it does turn out that sometimes when you form new bonds, you get a lot of energy out, and so in the end, you might get more energy out than you have to put in. But you always have to have a little bit to put in, no matter what reaction you're talking about. So that's called a minimum amount of energy. So here are some examples. This is kind of an example of orientation. So let's say we have two NO molecules, or an NO molecule reacting with an O3 molecule to give us NO, NO2, and O2. So you can see on the top row that the oxygen is red and the nitrogen is blue. So if the oxygen hits the center atom in the the O3, nothing happens. It's an ineffective collision, they just bounce apart. If the N attacks the center O3, again, in ineffective collision, they bounce apart. It looks like, from what they know about this reaction, if the N collides with one of the end oxygens in O3, then a collision will occur and one of the oxygen atoms will transfer over to the N. So not only do if two O3 molecules collided with each other, of course this reaction wouldn't happen, or if two NO molecules collided, but not only that, they have to be in the correct orientation, so the right part of the molecules have to collide with the other correct part of the molecule to make it happen. So an effective collision results in a reaction in the products being formed. Now, the amount of energy that's required to get the reaction going is called the activation energy, the energy required to activate the reaction. So unless you have enough energy around, the molecules will bounce off each other no matter their orientation. So not only does the correct molecules have to collide, they have to collide with the correct orientation, but they also have to have enough energy in order to break bonds and form new bonds. We can use an example of a kitchen match. You could hold a kitchen match in front of you all day and it's not going to just burst into flames. They will burst into flames if you rub it on a rough surface. Well, the process of rubbing that match on the rough surface gives it enough frictional energy to get the match started. And then once it's ignited, of course, it's hot, and so there continues to be plenty of energy to continue to burn without help. So there has to be something, generally speaking, to get the reaction started, and that is called the activation energy. This is a graph of a reaction. This is called an energy diagram. And so if you look at this graph, on the left-hand side of the graph, you can see that we have the reactants. And notice on the y-axis, we have increasing energy. And on the x-axis, we have reaction pathway. So what that means is just during the process of the reaction from start to finish. So on the left-hand side, we have the start of the reaction, we have the reactants. Now notice that they start kind of at a high energy. They don't start down at zero, but they're they kind of hang out. Then, as the reaction occurs, they start to get closer and closer to each other. They require activation energy, and so as they get closer and closer, they start moving up to the top of the hump. At the top of the hump is something called the transition state, and that's the point where new bonds are starting to be formed, old bonds are starting to break. It's the highest energy of this reaction. So you can see from the energy of the reactants, the start of the reaction, up to the top of the hump, that amount of energy is the amount that is required to get the reaction going, and that's called the activation energy. Once the molecule is in the transition state, or the molecules are in the transition state, what will happen is so the new bonds will form, the old bonds will break, and they'll start to pull apart from each other, and they'll head down the hill until they get to the bottom, and you can see energy of products. In this case, the energy of the products happen to be lower than the energy of the reactants. The amount of energy for the whole reaction is found by starting at the energy of the reactants and going to the energy of the products. So notice that the activation energy isn't really included in the energy of the reaction. The activation energy is required, but we have to put that much in, and then we get some back. We get all of that back plus some, and so the overall energy action is just from the start to the finish. Okay. So here are two examples of reaction diagrams where the energy of the reactants and the products are different. So in the graph to the left, you'll see the energy of the reactants, A and B. Then we have E with the little a, it stands for activation energy. So the activation energy makes it go up to the top of the hump. From the start where A and B are up to the top of the hump is the activation energy. Then as you come down the hill, notice that C and D, the products, are actually lower energy than A and B, like the one we just saw on the previous slide. This is an exothermic reaction because energy is given off. Energy has been released. So to go from A and B to get down to C and D, we go to a lower energy, which means energy had to be given off. That's exothermic. The energy of the reaction is negative because we're going down. So the delta E, or sometimes we also say delta H for heat of energy, is negative. So the one on the left is the exothermic reaction where the products are at a lower energy than the reactants. The graph to the right is an endothermic reaction. So this time you see A and B are kind of low down. They have a little bit of energy. Then to get to the top of the hump, you're going to need to put in a lot of energy. So the activation energy is high to get to the top of the hump. And then once the transition state is there, they break apart to C and D, but now C and D are at a higher energy level than A and B started out as. So overall, even though you had to put a lot of energy in to get to the top of the hump, you do get some of it back by coming back down the hump, but you don't get all of it back. So overall, you have to put some energy in, and that's the arrow all the way to the right, where it says E is greater than 0. The energy from A and B up to C and D is positive. You had to put some in. That's an endothermic reaction. So you need to know the difference between these two graphs. What does an exothermic reaction look like? What does an endothermic reaction look like? And you should be able to label a graph, like with what is the activation energy, what is the overall energy, where is the transition state, what are the reactants, where are the products. All right, so keep in mind that to break a bond always requires energy, and forming a bond always releases energy. So they're opposite, and it generally is the same amount of energy for the same kind of bond. If you have to break an OH bond, you have to put in a certain amount of energy. If you form an OH bond, you get the same amount of energy out. But overall, whether a reaction is endothermic or exothermic will depend on the balance. So let's say the reactant bonds are really strong. You have to put a lot of energy in to break them. And then the product bonds are weak, and so when the new bonds are formed, they only release a little bit of energy, so you don't get very much back. You have to put a lot in, and you don't get very much back out. This is an endothermic reaction, so overall, you had to put more energy in than you got out. What if the reactant bonds are weak? If the reactant bonds are weak, it doesn't take very much energy to break them. And then if the products are strong bonds, they will give off a lot of energy. So if it takes a little bit to break them and then you get a lot back, then overall you will release energy, and this is an exothermic reaction. So if you're thinking about, like you always hear, oh, there's energy stored in those bonds. Well, it really is a balance between what kind of bonds they are. So if you take a sugar molecule in your body, those are actually kind of weak bonds, the C bonds and the O bonds and the H bonds. So you do have to have a little energy to break down the sugar, so your body is already warm and you're kind of breaking down the sugar. But what happens is then once they break down, so you have to put a little energy to break them down, the new bonds that are formed, the H2O and the CO2, are really strong bonds, and so a lot of energy is released. So you are removing the energy that was stored in those bonds. It's just not quite the way biologists sort of say. You do have to put a little bit of energy in to break it, and then you can get a lot out. So overall, you can get a lot out. Now, these two graphs represent different amounts of activation energy. The one on the left, you can see is sort of a little hump. This is low activation energy. And the one on the right has high activation energy. You can probably imagine that if something has low activation energy, that reaction will more likely happen, or at least it will happen quicker. So it doesn't take as much energy, it's more likely to happen, it will happen quicker. And so generally speaking, if you see a little hump on a energy diagram, that's a quicker reaction. If you see a big hump, that is a slower reaction. So a slow versus fast reaction, that is the rate of the reaction rates. The study of reaction rates is called kinetics. And so what are things that influence the rate of the reaction? So we know already how reactions occur. We know how they're exothermic or endothermic. But why do some reactions go really fast and others go really slow? You know, you could sit all day watching a nail and you won't see it rust. You come back a few weeks later and it could be all rusty. So obviously the reaction has happened, but very slowly. On the other hand, you can have, you turn on your propane tank and it explodes into gas, into flame. So that's a very quick reaction. So what are some things that influence the rate of the reaction? Well, here they are. The nature of the reactants, the concentration of the reactants, the temperature of the reaction, and then the presence or not presence of a catalyst. So let's look at each of those individually. The nature of the reactants. It depends on the kind of reactants involved. So for example, if you have a reaction between ions, positive and negative charges, they react very quickly because they're very strongly attracted to each other. Opposite attracts. However, covalent molecules, where bonds have to be broken, often occur much slower. That's because they only collide due to random motion and they're not really attracted to each other like ionic compounds. Some, like polar molecules that have some attraction for each other, will fall in the middle. They'll kind of be moderately fast. It sort of just depends on the molecules. Some other things about the reactants. The physical state can really matter. So for example, if you're trying to react a solid and a liquid, of course they have to be in contact with each other. So the nature of the reactant can be very important. The next slide, the molecular or something like that. So this kind of leads into the next thing, the concentration of the reactants. This can kind of overlap the condition of the reactants, the nature of the reactants. So anyway, a reaction occurs between two molecules. They have to collide. So the concentration can also be very important. The higher the concentration of the reactants, the more likely you'll have collisions. And the more collisions you have, the faster the reaction. So you can see in the picture with the molecules, low concentration has a few collisions. On the right, higher concentration means more collisions, and so reactions happen faster. Surface area is also an aspect of concentration. It's a little bit of an aspect of concentration. It's a little bit of an aspect of the nature of the compound, which we saw on the previous slide. So the fact that steel wool is chopped very finely means that it has a lot of surface area. So if it's reacting with something in the air, it can react, if there's a lot of surface area, it will react faster than if you have one big hunk of iron. So a solid piece of iron will happen slowly because it doesn't have a lot of surface area, whereas steel wool will likely react faster because it's got a lot of surface area. And if you were trying to burn it with oxygen, like light it on fire, the steel wool would probably burn pretty quickly, whereas a iron nail would not. So surface area is one aspect of concentration. But another thing that you might consider, say, concentration. So if you light a fire in the room where you have a little bit of oxygen, we know that the match will burn. What if we put the match near a tank that's pure oxygen, much higher concentration oxygen? You can imagine that you don't want lit flames by a tank of oxygen. It'll explode because there is so much more oxygen. The reaction will happen so much faster than in just pure air. Okay, temperature is another thing. Generally speaking, if you increase the temperature, the reaction will happen faster. First of all, there will be more collision. So if you're thinking about something that's happening in the air or in a liquid and you heat it up, the molecules start moving faster. If the molecules start moving faster, more collisions will take place. Because they're just colliding with each other more often, they're just hitting into each other, they're moving faster. But in addition to that, if the molecules are moving faster, they have more energy. When they collide, they're more likely to collide with more force, which means more of the molecules will have the minimum activation energy. And so both of these ways, temperature will increase the speed of the reaction or the rate of the reaction. So first of all, there's more collisions because they're moving faster. Second of all, they collide with more force. And finally, the presence of a catalyst can also speed up the reaction. What is a catalyst? A catalyst is a substance that speeds up a reaction without being used up in the reaction. So it gets used in the reaction, but then it is regenerated or the reaction leaves it alone once it happens. A homogeneous catalyst is one that is distributed because they're in the same phase. So if you had a liquid reaction and you put a liquid catalyst in there, that would be homogeneous. A heterogeneous catalyst is usually, there's two different phases, but usually what happens is you have a solid with a large surface area and it's placed inside a liquid, or if you've got air around for the reaction, like a gas and a solid. Those would be, if they're in different phases, that's heterogeneous. Now, a catalyst will speed up a reaction in two ways. First of all, what they do is they provide an alternate reaction pathway with a lower activation energy. So you can see in this little graph, the red line is the activation energy for this reaction without a catalyst, so very high. If you add a catalyst, the hump will be much lower, meaning you need less energy to make it happen, and so it will happen faster. They also sometimes can provide a surface on which to allow the reaction to happen. So sometimes what you'll have, like if you're trying to, like a catalytic converter, what it is a piece of metal, and it's trying to convert carbon monoxide to carbon dioxide so that we don't have so much carbon dioxide pollution in the air. So what happens, it's a surface area, so now the carbon dioxide has to react with oxygen, or the carbon monoxide, I'm sorry, has to react with the oxygen to form carbon dioxide. So one way that can happen is if the two molecules collide. If you have the catalytic converter, the piece of metal there, the carbon monoxide can attach itself, and then a little while later an oxygen can attach itself to that same piece of metal. They can attach themselves close to each other, and so now they're in the right orientation and they're near each other, and so they can react. So it's not as much random collisions as a place for reaction, for molecules to come together to react. So that's another way that a catalyst can speed up a reaction. Enzymes are just catalysts that happen to be in a body. So if you think about so many chemical reactions that have to happen in the body, some of them will occur, I mean, of course our body temperature is higher than the air around it, but we would have to be much, much hotter to allow a lot of the reactions to happen that actually do happen in our bodies. So that's why our body has so many catalysts, which are called enzymes. Enzymes will increase the rate of the reaction, often 10,000 to, you can see there, 10 to the 17th, I don't know what that is, billions and trillions of times. So generally what happens with an enzyme is that you have an active site, and sort of what I was saying before with the piece of metal, the active site is shaped in such a way that either the two parts can come together, or the thing that has to be broken apart can fit into the enzyme site. Then the reaction is allowed to occur, and then they're able to go their own ways. Or you could almost think of it as the other way around. The two can come together into the location, the reaction can happen to bind them together, and then they're formed. So the enzymes have this active site, which is a pocket or a groove, which allows the molecules either to bind together or to break up. And so it lowers the activation energy of the reaction. All right, so we have actually one more topic to cover, and this is a little bit different. So that last topic was kinetics, which is the rate of reaction. And our last topic is going to be chemical equilibrium. So lots and lots of reactions go to completion. So if we strike a match and it burns, it goes to completion. If we take a piece of wood, eventually it will burn all the way to ash. So that means that the reactants are completely converted into products. Many reactions, though, are reversible, which means that both the forward reaction can occur and then the reverse reaction can actually occur as well. When this happens, we say that the reactants and products are in equilibrium. So you see here the example, hydrogen reacting with iodine. So they may react together, and then after a while, some of the HI may break apart back into H2 and I2. So it's not a complete reaction because it can go both ways. So H2 plus I2 to give us 2HI is the forward reaction. So when they combine, they'll form 2HI. And if we put into a reaction container the H2 and the I2, there's a lot of them around. They'll start reacting and they'll start forming HI. Well, after a while, the reaction will slow down. Well, why is that? Because the molecules are being used up. Remember that we say the concentration will speed up the reaction. Well, the opposite is true. If the reactants start getting used up, there's fewer of them around, and so the reaction will slow down. So the forward reaction will start to slow down. Well, also keep in mind that the products are starting to build up. There's more and more of them. And now if this reaction can happen in the reverse, some of those HI molecules will start, there's more and more of them, they'll start to break apart, and the reverse reaction will start to increase. Well, at some point, the rate of the forward reaction will equal the rate of the reverse reaction, and then the concentrations don't change any longer. They become constant, and we're said to be in a state of equilibrium. So a lot of reactions will do this. They won't go all the way to the end, but they'll kind of stop halfway, and you'll have some reactants and some products, and they'll kind of stay stable. A reversible reaction, generally, you have a mixture, like I just said, a mixture of reactants and products all together. And it doesn't matter if you started with the reactants or you started with the products, they usually end up sort of in this equilibrium at a certain place, no matter which way you started. Let me just give you an example of an equilibrium. The elevator is at equilibrium. So let's go through that. So let's say you are watching an elevator and you can only see between floors what's happening. It's like a glass elevator. You can't see it as it goes up or down. Well, so say it starts up, you see that there are 8 people in the elevator, and then when it gets to the second floor, 2 people get off and 2 people get on. Well, from afar, you still see 8 people. So then, let's say at the 3rd floor, 5 people get off and 5 more get on, but then you see them between the floors and you still see 8 people. From far away, it looks like nothing has changed. That's equilibrium. So it's also, there's a term called dynamic equilibrium, because actually things are changing. People are getting on, people are getting off. You can think of that as a reaction. Reactants react, or products react backwards. They're getting on and off. Overall, everything looks the same. So it's sort of the same thing. Reactants can react and products can still react, and so even if it's at equilibrium, you have a reaction taking place both ways, but it doesn't look like the concentrations are changing, because if 2 reactants react, a product might react backwards in the same ratio, and so overall nothing looks like it's changing. Okay, so depending on the reaction, the equilibrium can lie to the right or lie to the left. So what does that mean? The position of the equilibrium is an indication of whether products predominate or reactants. So it could be smack in the middle, and you might have a half and half, or products might be more favored, in which case the equilibrium lies to the right. Or if reactants are more favored, the equilibrium can lie to the left, meaning you have more reactants than products. So an equilibrium, just depending on the reaction, can lie smack in the middle, or it can lie to the left, or it can lie to the right. Now you can do things to, if something's at equilibrium, if a reaction is at equilibrium, it can actually be messed up. There are ways that you can change an equilibrium and make it shift, or so factors that influence the position of the equilibrium. So let's say you have a reaction that's going on and you want to produce more products, but the reaction sort of favors, it lies to the left, and it sort of favors the reactants. Well, there's things that you can do to influence the position of equilibrium. Le Chatelier was a man who studied equilibrium, and so they named this principle after him, Le Chatelier's principle. And Le Chatelier says that the position of equilibrium will shift in response to changes made in the equilibrium, or to the equilibrium. So here's some factors that can change which way an equilibrium lies. The concentration of the reactants and products, the temperature of the reaction, and possibly catalysts. So let's look at each of those. In general, a shift will happen away from the side which something is added, or toward the side from which something is removed. So let's say we have reactants and products in equilibrium, and then we add some more reactants. We just kind of pour some more in. Well, what's going to happen, all of a sudden the equilibrium is messed up, and there's too many reactants. So what's going to happen is the reaction will proceed toward products. It'll move toward the right so that more products are formed, so that it will shift to the right. So if you add a reactant, it will shift the equilibrium to the right toward the products. If you remove some reactants, then what's going to happen is the equilibrium is going to say, wait, we're off, and so they're going to try to make up the reactants that were removed, and so the reaction will shift to the left to try to replace the reactants. If products are removed, the reaction will go toward the right, toward products, to try to replace the products that were removed. If products are added, the reaction will shift to the left to try to get rid of the extra products. So if you add something to one side, it will shift to the other side. If you remove something from one side, it will shift toward that same side. What happens if you change the temperature of something at equilibrium? Well, it depends on if the reaction is exothermic or endothermic. So let's think about that. If we're increasing the temperature, what we're really doing is we're increasing the heat. We're adding heat. So if the reaction is an endothermic reaction, that means heat is a reactant. So if we increase the temperature, we're really increasing a reactant. And so what happens? The reaction will shift toward the products to the right. If the reaction, however, is exothermic, that means that heat is a product. So if we increase the temperature, we're increasing a product, and so it will shift toward the reactants, toward the left. So the reverse is true if we cool something. If we cool it, if it's endothermic and we cool it, it will shift toward the reactants to try to get more heat out. So if we're removing a reactant, it will shift toward that side. If it's an exothermic reaction, again, heat is a product, and if we cool it down, we're removing product, and so the equilibrium will shift toward the right. So it's a little bit complicated. It sort of depends on if it's exothermic or endothermic. But again, it's the same idea. If you remove a reactant, it will shift toward that side. If you add a reactant, it will shift away toward the other side. So if you know which side of the reaction the heat is, exothermic is a product, endothermic is a reactant, then if you add it, it will shift away from that side. If you remove heat, if you cool it down, it will move toward that side. Finally, a catalyst does not change the position of equilibrium, so that's all we need to know. They do lower the energy barrier, but it lowers at both sides, and so it'll speed up the reaction, but it will never change equilibrium. So that's good to know. We don't have to... All right, so let's look at an example. This is an endothermic reaction, and it's at equilibrium. So let's say we heated up this reaction. Will equilibrium shift, or will it stay? Which way will it shift? Well, if it's heated, what does that mean? We're adding a reactant, because heat is a reactant. So if we heat it up, it's going to want to shift away from that side. So it's going to shift toward the right to products. All right, second bullet. What if we remove NO2? Well, if we remove NO2, NO2 is a reactant, so if we remove it, it will shift toward that same side. So it will shift to the left to try to replace more of the NO2 that was removed. What if we add NH3? Well, if we add more NH3, NH3 is a product. If we add more of it, it's going to shift away from that side. So again, it will shift to the left to try to balance out the extra NH3 that was added. But if a catalyst were added, well, the equilibrium position would not change. So we don't have to worry about that. All right, so that is the end of this unit. It was a nice long one, but hopefully you learned a lot. and onward to Unit 9.